All right, we're looking today at properties of coefficients and in particular a few proofs that surround the Pascal's triangle. The first proof that we're proving here is that n choose 0 is equal to n choose n, which is equal to 1. That's the proof that proves that all of the rows in the Pascal's triangle start and end with the number 1. So how do we do it? Well, this line here I've highlighted in red, that's just our definition. If we were to expand a plus x to the n, you've seen this. This is just the definition of how we would do it. From there, to do the proof, what I'm going to do is let a equals 1 and x equals 0. So replacing all of the a's in here with 1, all the x's with 0. And I get something that looks like this. 1 plus 0 to the power of n, which is then on the right-hand side, I've got this big ugly thing. What I notice though, each term is timesing by 0. So which is why we get these zeros here, okay? And from there, we're left with just 1 is equal to n choose 0. So therefore, 1 is equal to n choose 0 in our proof. It's not our full proof done yet though, because all we've done so far is solve that n choose 0 is equal to 1. Now we need to show that n choose n is equal to 1. How do we do that? Well, now instead we will let a equals 0 and x equals 1. So fill that into my definition up here I've highlighted in red. And I get this long line here of working. What do I end up with? That 1 to the power of n is equal to, and all of these again have zeros in them. The zeros multiplying by each term so they cancel out. So I'm just left with n choose n timesing by 1 to the power of n, which you can see here, and I've highlighted so it's a bit easier to see. It must mean that n choose n is equal to 1. So therefore, I've just written in green here, if n choose 0 is equal to 1 and n choose n is equal to 1, they're all equal to 1. The next proof we're looking at then, this one's a bit nicer. This one proves the symmetry rule in the Pascal's triangle, okay? And it's saying that we're going to prove that n choose k is equal to n choose n minus k, okay? And that's that symmetry on our line of Pascal's. So we start with the definition that we know. The formula for n choose k is this. So then all I'm doing is I'm subbing in n choose, and instead of k, my k value is n minus k. Okay, so in my formula, wherever there was a k, I'm replacing then with an n minus k, and that's what you can see here in this line. And it cleans up pretty nicely because my n take away n gives me nothing, so I'm left with k factorial times by n minus k factorial, which is the definition again. So therefore, even when you sub in n choose n minus k, you get back to the original definition, so therefore n choose k is equal to n choose n minus k. All right, so those two aren't too bad. We do get a little bit more complicated with this one here. Now, after I haven't looked at this for a while, it does take me some time to just click back through every step, but I've tried to show in colours and things exactly what I've done. So pause the video if you want to write it out first, but otherwise I'm just going to jump straight into the proof. Okay, so the first thing I do is I break it up. Left-hand side is equal to, well, write an expression for n choose k. That's just my definition, my formula there. So now I need to make this right-hand side to somehow, when I sub it in as that is my n value, that is my k value, plussing it with that is my n value, that is my k value into my formula, it needs to somehow come back and look like my original formula. That's what the proof is asking me. So I've highlighted here so you can see exactly what I'm subbing in. Remember, I'm just subbing into that original combinations formula, which you can see over here on the left, okay? So I just take my new n and k values and I'm putting them into this formula, and that's how I'm getting these two fractions here. So I write it in, subbing it in exactly how they are into the formula. And I then start looking how I can clean it up. Straight away I'm thinking I got two fractions here and I need to get them to be the same denominator. That's the way I need to plus two fractions. So once you sort of gather some like terms here, you can see that I end up with my -1 here in yellow, minus and -1 will cancel each other out. So that leaves me with my denominator here. And this side doesn't really clean up much, so I've rewritten it out. But it's how I then went from this line to this one, which is, and then again to the next one, what I guess the trickier part of this proof is, okay? Keep in mind, I need to get these two fractions here to have the same denominator so I can plus them together. So how am I going to do that? Well, these little manipulations that I've done here in the colours. Let's start by looking, okay, well, over on my fraction on the left, I've got k minus 1 factorial, where this one I've just got k factorial. However, how can I manipulate it? I know, and notice what I've written here, k minus 1 factorial, if I just times that by k, I would have k factorial. Okay, because think, 5 minus 1 factorial, that's really 4 factorial. But if I just times it by a 5, then suddenly that's 5 factorial. So that's all that's saying there. So what I can then do is, instead of having a k there, I could replace it with k lots of k minus 1 factorial. Then I've got the k minus 1 over here and a k minus 1 there. So I'm getting closer to the same denominators. As for this part, I've underlined it in pink. This is my working for it. A very similar method to what I just did with the k's. I said, okay, well, n minus k timesing by n minus k minus 1 would just be equal to n minus k factorial. It's the exact same idea that I just did here with my k's in yellow, that if you're subtracting 1, if you just times by that original part, it's that factorial. So once I had that line there, I wanted to rearrange it to make an expression to replace my n minus 1 minus k. So I rearranged it, and I brought the n minus k over and divided. So now this gave me an expression here for how I could replace n minus k minus 1 factorial. And that's exactly what I do on my next line. So now have a look at this next line down. Notice what I did. Okay, the left-hand fraction is the same. The right-hand fraction I've substituted in. So take a moment now, just have a look and see. All right, okay. So hopefully you fill that in. You can see now that I've just replaced the pink part with what I worked out as the expression up here. And I've replaced the yellow with what I worked up out here. Now, what did I do to get to the next line of working? Okay, so to get to the next line, so that's me going from here to here. What do? Well, I cleaned up the fraction on a fraction. Okay, so this part here, I'm just flipping and timesing. All right, so it just took the denominator up and times it with the front, which is what this next part here is. That's that denominator. Okay. From there, I'm looking and going, okay, the denominators are getting pretty close now. I just have to multiply by what's missing, right? So I said, okay, well, the left-hand side is just missing the times k. So times the top and bottom by k. And now suddenly I've got my two denominators the exact same. I can write it out all as 1. When I write it all out as 1, I now am going to come back and say, well, I know I could clean up k lots of k minus 1 factorial is really just k factorial. So I clean that back up. Then from there, I factorise my n minus 1 factorial out the front. So you can see n minus 1 factorial, n minus 1 factorial, and boarded out the front here. Which then allowed me to clean up things quite nicely from there. And where was I? Yep, so again, that was my factorising at the front, which left me with this on the inside, and the k minus k cancelled each other out. So I was left with just, n outside of n minus 1 factorial, which I know that n timesing by n minus 1 factorial is really n factorial. Notice we use that property quite a lot in this one proof, which then gives me the left-hand side, and I got it. Pretty complicated there. We used that one property over and over, which I explained back here in this part with the 5 factorial, okay? So I'll just go back over it that if you had 5 minus 1 factorial, that would give me the same as 4 factorial. If I then times it by 5, then it's 5 timesing by 4 factorial, which we know is really just 5 factorial. So anytime you have something timesing by that something minus 1 factorial, it's really just that something factorial. We use that, 3 times in that one proof. Okay, it's the key idea there to be able to manipulate it. All right, from here, the next page, much nicer. And now that you've established those proofs, we're just looking through some basic examples here. If we are proving something equals something else, you can see this one's going to be proving the symmetry. We know that showing anything or proving anything that involves numbers is much easier than when it doesn't. So all I have to do, split it up. Left-hand side, work that out, put it in your formula. Right-hand side, put in your formula, and voila, I get it. The next one down here, remember our brackets is the same as this form here that I've rewritten out with my C's. This one is actually the proof that a number in Pascal's triangle is the sum of the two numbers above it. Okay, and you'll see that when we fill it out, but I like to rewrite it out in this form, just helps my brain register it. So again, start with the left-hand side, I clean it up, then I go to my right-hand side. I fill both of those two things into the two different formulas, into two formulas. Then what I'm looking at here is how can I plus two fractions, again, similar to that proof, but much nicer. How can I plus two fractions, denominators are different? Well, how can you manipulate it? If I times a 3 factorial by the number 4, I got 4 factorial. So I times this by 4, but whatever I do to the bottom, I must do the top. Same as 2 factorial. If I times 2 factorial by 3, I now have 3 factorial. So whatever I do to the bottom, I must do the top. Notice how now my denominators become the same, 3 factorial, 4 factorial. But I have up the top here 4 lots of 6 factorial, 3 lots of 6 factorial. So I just factorised out my 6 factorial, which gave me 6 factorial timesing by 7 in here. And I know that 7 times by 6 factorial is 7 factorial. And there you go. That was what the left-hand side was. And last one we'll look at is, okay, looks more confusing than it is. I like to rewrite it out, thinking about it in my combination form with my C. This one's proving that symmetry. So sub it into the formula on the left-hand side. Now I just know I have to make the right-hand side look like that. So again, that is then the same thing as n choose n minus k. Just essentially the same thing as what we did earlier. It's just given in a different format. Sub it into my combinations formula, being very careful when I sub it in. N minus n cancels each other out. So negative and negative make positive, k factorial, n minus k factorial, which is equal to the left-hand side. I should then write a therefore statement. Therefore, nk, I always go to write it as a fraction, is equal to n minus k. But that was it today. It's just going over those proofs. Our next lesson is our final lesson, where we're just going to look at some more things to do with the coefficients, and then that finishes the topic.